So next up is by the numbers. T-Mobile drives data center density with direct distribution power. Paul?
Thank you, Dave. This will be an illustrated discussion with T-Mobile's Don Doyle about T-Mobile's development of a direct distribution power architecture for their new data centers. I'm Paul Smith, and I'm with ABB's electrification business, previously GE, Lineage, Tyco, and Lucent, where I've been in an applications engineering role for the last 22 years. My work includes product development strategies, bringing new power technologies, including the utility-to-rack power systems for T-Mobile, that we're going to be discussing today. Don, would you like to give a brief introduction of yourself?
Sure can. I'm the Critical Facilities Engineering member of technical staff at T-Mobile. I oversee the planning and strategy for all of T-Mobile's data center and mobile switching offices across the U.S. I focus on design and operational strategies for uninterruptible power and cooling systems. I'm here today to describe a new direct power distribution platform, this design in our new Florida site. We'll be using it exclusively going forward.
Our session title promises a by-the-numbers take on T-Mobile's new data center direct distribution power architecture. Today we'll be talking about what is direct distribution power, how we arrived at this solution, when and where it makes sense, how it's implemented, and what sort of returns we expect to see. So before we get to those numbers, let's start with the question, what is direct distribution power? At a fundamental level, direct distribution is really just a direct-to-rack power shortcut. But in reality, it's so much more. Yes, the utility power is delivered directly to the equipment rack, but there is a very different utility delivery and backup architecture. As power engineers, we like to think we can solve the world's power needs with technology. But this new architecture is really a technology enabler to you, isn't it, Don?
That's right, Paul. This direct from utility to rack power architecture is really about enabling our new, very high power density equipment, including the newest virtual compute platforms. You can really think of it as a complete, redundant, and independent UPS system in each. We're getting well ahead of ourselves. Paul, can you tell us a little about what direct distribution power is?
Yes, I can. The traditional data center power system is often based on an AC UPS system, which supports the critical load during short utility outages, usually long enough to start a reserve power generator. Utility power is brought into the facility and converted to 480 volts three-phase AC power. This is converted within the UPS to about 540 volts DC and used to charge a battery bank. This DC power must then be converted back to AC, usually also at 480 volts, for efficient distribution within the data center. When power gets close to the user equipment, it's converted to 208 volts, single phase, by a transformer, usually in a local power distribution unit, PDU. This is then fed to the user equipment rack, where it's distributed to the servers, which convert the 208 volts to 12 volts DC for use within the server and storage units. This diagram illustrates this process and shows how the power is converted at 5 distinct stages. Each conversion is subject to small losses, and these all accumulate. Using the same diagram, we've shaded the parts which are not required to implement a DC UPS architecture. This has been used for decades in telecom service provider central offices and is also used to power network data centers. We can see that the shaded areas represent 2 distinct conversion steps, which are not required in a DC system. Removing these unused conversion steps, we see the much simplified power transfer of an uninterruptible power system using a DC battery plant-based system. This is what you've done in telecom switching centers for decades, right, Don?
Yes, Paul. UPS, DC rectifier plants, and battery systems all require substantial maintenance. They also require competent capacity analysis upgrades, age and performance reports, and safety inspections. I do love power guys. They travel to see me and are very well trained, and consequently expensive. I think I may know them too well. I know their hobbies, political views, even some of their kids. I kind of wish I didn't. If I could get rid of everything they do, I could avoid having to pay for all that. As our power densities increased, we ran out of room to run the cables. 48-volt DC power distribution requires lots of large cables, so it makes sense to do the conversion to 48 volts closer to the loads. During the evolution of these systems, we moved the rectifiers and batteries to the end of each row instead of the next room to reduce cable lengths. That change alone eliminated all 750 MCM cables, saving about $1 million per site. This revealed to us that eventually we'd need to move the batteries and conversion modules even closer to the loads into each IT cabinet. We needed much more power per cabinet, so higher voltage was needed. By selecting 480 volts AC power distribution, we maximized the power available from our low voltage utility source. Fortunately, ABB embraced this idea and developed the Edge system architecture to enable it.
Now power can be moved around the facility at the much more efficient 480 volts AC level, but only converted to 48 volt DC once it's very close to the using equipment. This minimizes the transmission losses as well as reducing the number of conversion steps in the overall system. As we said earlier, each conversion step incurs a small amount of loss, and it's the power engineer's job to make sure that these losses are minimized. While this DC powertrain is nice and efficient, Don, you also wanted to increase the reliability of power to your revenue-generating equipment by a significant amount, didn't you?
That's right. This AC power input scheme improves supply power reliability so much, an extended runtime battery system is no longer valuable. The battery capacity needed is reduced to only the bridge time for utility to generator transitions. We reduced battery energy storage by 85 to 97%. ABB's clever design places the rectifier and batteries in the space between the server rails and the side of the cabinet. If you look closely, you can see these are two fully independent power systems, which meet only at the server's power rails. This is the ultimate in power redundancy.
So in fact, you have a full dual redundant powertrain with backup power sources in each path, 4 independent AC sources, each capable of supplying the entire facility. And 2 utility feeds have to fail before the battery is ever going to go on discharge, and even then, only for the time that it takes for one of the 2 generators to start. Okay, now we understand what direct distribution power is. Don, why did T-Mobile choose to implement this architecture?
Yeah, it's a bit of a funny story. So a few years ago, our CEO thought it'd be a good idea to offer free pizza to all our customers on a Tuesday. On that fateful Tuesday, Pizza Hut broke sales records in nearly every store. Not the Tuesday records, but all-time records previously held on Super Bowl Sunday. Then he listened to customer complaints and systemically eliminated everything they complained about, all the while reducing the price. This led to a bit of customer growth, but a ton of usage growth. While customer growth is a linear function, data throughput growth is still exponential. The good news is that server and router throughput doubles about every 2 to 3 years. Our data throughput growth rate well exceeds the tech refresh rate, so our offices are still growing. Typically, new servers are double the compute capacity, but require only 30% more power. However, that 30% more power is within the same area, so that is an increase in power density that we must supply. If we kept with a UPS or telecom power system, we'd just continue with the same size, scalability, and cost issues as before. In two of our latest construction projects, we designed each site both ways. We found about $6 million in capital savings and 30% more cabinets within the same building area by using our DD3.0 design. This architecture does not segregate power systems. This example has maximum limits of 600 kW per single row and 600 kW per single cabinet, with adjacent rows and cabinets still allowed. We can support 5,000 kW IT load over about 500 cabinets in Data Hall 1 to average 10 kW per cabinet in that room, but Data Hall 2 will be much more dense.
Don, let me stop you for a moment because you mentioned high-density digital equipment and requiring more power before, but what you just said is mind-boggling for a humble power engineer. You said you can get twice the compute throughput with only 30% increase in power. Here we are in the powertrain business trying to check out 1% or 2% of improvement in efficiency, and you've just saved a whopping 35% on your power bill by using this high-performance equipment. It would appear I'm in the wrong business.
Yeah, well, maybe we both are. Your numbers are accurate, but don't give up your day job yet, because that high-performance equipment still does need more power. And it needs it in smaller and smaller spaces. So our power density is growing rapidly. You can see that in the power per rack numbers, which only a few years ago were in the 4 to 5 kW per rack range, and are now 12 to 16 kW per rack, and will certainly increase. The direct distribution power system is an important enabler for that density increase.
That's pretty compelling, Don. But how did T-Mobile make this transition from a centralized power to direct distribution? That surely couldn't have happened overnight.
Yes, it surely didn't. So this is 3 slides in one. If you start at the left, we phased this in over a period of 10 years, making our proof cases over time. Everyone in telecom started with a single bulk DC power plant, and many in data centers started with a single bulk UPS system with the utility bypass. From an architecture perspective, they're similar. Everyone worked really hard to ensure these bulk systems were extremely reliable. That was important because a single failure could get us on the news. Failure did still occur until much better redundancy designs were used. Our power density increased so much that we couldn't fit the primary distribution cables. I could either move 30 offices to new locations or I could find a solution. We moved the batteries to the end of each row. This eliminated massive amounts of cable and saved more than enough money to pay for our distributed power plants. Dual system failures were now limited to a single row. Now our DD3.0 architecture has moved the rectifier, battery, and PDUs all into the IT cabinet, resulting in 30% more cabinets within the same space, concurrent maintainability, plug-and-play repairs and capacity increases, and a dual failure takes out only one cabinet. Getting direct distribution power down to the cabinet level required a new power platform, which led to our working with ABB on their Edge power systems. Paul, can you give us a quick view of what Edge is and how we replaced a few plants with hundreds of cabinet-based systems?
I'd be happy to, Don. Let's look at what makes up the ABB Edge distributed data center power architecture and how it fits into this new direct distribution power architecture. At the heart of the system is a server cabinet that puts all the power conversion, battery, and distribution and controls into the sides or the edge of the cabinet. Duplicating the power systems within the cabinet allows the true two-end redundancy to be implemented. Accessed from the front of the cabinets are the rectifiers, batteries, and controller. They're all modular and designed for plug-and-play simplicity of installation and maintenance. You no longer need specially trained power personnel. At the back of the rack is a power distribution rail that allows plug-in power distribution modules. So you just plug in the number that you need and can add more if they're needed. By putting the power equipment in the edge of the rack, it keeps the entire rack height available for revenue-generating equipment. The result is savings in space and costs, and I'll let Don talk about that a little more. So Don, what does this architecture allow you to do that you haven't been able to do up to now?
I had to find the mute button again. Here's a depiction of the 1.3x power equal 2x computing capacity relationship. And this is the divergence in the lines. It's quite extreme. Notice how the power density does increase over time, but the compute power increases at a much quicker exponential rate. Not only is this a cost savings, but it's also a capability advantage. Our network guys really like all the uber cool features in new servers. I got that from a young guy. We must allow our network designers the flexibility to select the most powerful and efficient machines available. If I can let them use virtual compute equipment, we can save another 40% off the cost of compute gear, eliminate dedicated hardware, and reduce the installation of apps to a remote point-and-click exercise.
So you can save money on the equipment as well as on the power usage. That's great. So one of the obvious advantages of this system is the elimination of the centralized power system and its construction costs, whether it be AC or DC UPS. But the implication is a much reduced battery backup capacity. You've specified 2 minutes in your systems. I want to look at some of the concerns that may have been raised at this drastic change. Don, what sort of reactions have you gotten along this journey?
Yeah, the reactions kind of range from befuddled to hysterical. Let me answer that first item with a question to our audience in general. When was the last time you actually had a battery discharge event? I know for me, I haven't seen a battery discharge event in any of our facilities across the whole country in the past 5 or 6 years. We stopped having these events when we added an N+1 generator redundancy scheme. In addition, our latest 2N generator strategy is even more reliable than that. With direct distribution architecture, we're replacing a giant battery plant with 4 independent AC sources, dual utilities, and dual generators, any one of which can support the full load if needed.
Don, I don't think the impact of that can be overstated. 4 independent AC sources. So you can do maintenance on one of those sources, and the load doesn't even know you're in the building.
You sure can. We can do maintenance on 3 of those sources, and nobody would be the wiser. Our Florida site is actually in a hurricane-prone area, as you might imagine. We even put all the A-side utility transformers, generators, and electrical gear on the north side of the building, and the B-side equipment is on the south side. There's literally a building between the A and the B systems. It may sound extreme, but the cost to do it was negligible.
Don, what about locating all those batteries inside the cabinet? Are there fire and safety issues, given now that hundreds of batteries will be located next to the servers?
I actually thought that was going to be the showstopper, and that's actually where I started in this analysis. I was at the battery conventions on the hunt for a safe battery. It's almost an oxymoron. But I didn't expect to find one, but I was giving it the college try. But my findings were actually to the contrary. So ABB stepped up, and they figured out that there's a way to actually accomplish this with the VRLA battery module. VRLA is really very good at delivering high power, and then for a short period of time, especially if you use a much smaller battery, and that's what they did. So each of the battery modules is monitored and controlled with an internal BMS that reports and protects each battery module. Now, I know what you're thinking. I don't fully trust battery controllers to keep us safe. So in addition to the onboard controllers, we determine the battery is intrinsically safe as well. By that I mean it cannot burn. Even in the worst case failure scenario, the total heat possible from the battery is less than the heat required to melt the metal battery enclosure. And it cannot explode. Hydrogen concentration must reach 4% to be combustible. The maximum hydrogen concentration within the battery module possible is 1.5%. We even cut the top off one of the cell packs to prove all the liquid acid is suspended. Even if an internal cell pack ruptures, no liquid should escape the battery module.
But Don, in a typical MSO, direct distribution means going from managing one large central power plant to now managing 100 or more small power systems. That prospect must have met with some, dare I say, skepticism?
Yeah, skepticism. One of their favorite operations manager went to ABB to take a look at the Edge platform. And all the way on the drive over there, he had lots of choice words and phrases about me, how I was a bad guy. That's because he had actually just got through the task of creating EPA reports. It's a mundane task you do once a year, and it gets in the way of everything. And so then when he got to ABB and looked at the system, he found out that all the data is readily available on the network. We have developed offboard tools to gather, analyze, and report capacity, performance, inventory, and required EPA reporting, all from the comfort of your chair. All these issues. I'm sorry. All these issues.
So he doesn't have to go. He doesn't have to go around and check on each of those individual batteries.
Well, yeah, and he had just finished that task, and it got in the way of everything else he was planning on. So he was plenty mad.
Yeah.
But when he discovered how easy his life is going to be going forward, I won a fan, let's say. All these issues used to require audits and specialized people to analyze. Now it's all done automatically.
Don, it sounds like you convinced all the power guys and the IT guys on this. What about the money guys? We all know that the technology may solve problems, but it must have a payoff, right?
Oh, yeah, sure. Well, you can't do anything unless your CFO says you can. So in the CapEx side, our initial CapEx is actually reduced. To be fair, mostly that's because of the extreme scalability. We only buy as much as we need on day one. Expansion is so easy that there's actually no project required. Essentially, we have reallocated the UPS or battery plant and electrical switchgear capital to add a generator and a utility instead. All future UPS and or battery project and battery plant capacity upgrade projects are eliminated. In our samples, we saved about 20% CapEx if we only compared the initial electrical systems costs.
We've talked about direct distribution as a core enabler for your entire high-density computing architecture and some CapEx issues. What are you seeing on the OpEx side of the ROI equation?
Well, firstly, installation. Installation is insanely fast. It kind of sounds like a lot here, but if you've ever installed some cabinets, you'll know. We just roll a pre-stuffed cabinet from the dock to its assigned floor space, raise the wheels, bolt it down, ground it, stab into the power bus, and connect twist lock for power. You can measure the time in man-minutes instead of man-hours. Then maintenance and safety helps a lot. They're all plug-and-play components. Rectifier and battery modules are all alarmed. Just replace the unit in alarm with new. You don't even need to know anything about power. Personnel are always isolated from all electrical conductors. There are no specialized personnel needed, and no PPE requirement.
Don, thanks for a well-illustrated conversation and step-by-step explanation of T-Mobile's early progress to migrate to direct distribution DC power. Before we take some questions, is there anything else you'd like to cover or maybe summarize about direct distribution power?
Yeah, don't get me started. Exponential rise in computing throughput. I want to reiterate that this is not just an alternative power approach. We were not trying to trim 1% in power losses. I think we did that, but it's really a moot point. It was instead to enable our high-density computing architecture. Scalable power. We needed to keep up with the compute refresh rate of every 24 to 36 months without expanding a centralized power system. With this design, we can easily accommodate a 3 kW cabinet next to a 24 kW cabinet, literally anywhere on the floor we choose. We can even power every cabinet in a row at 30 kW if needed. All this flexibility without any power upgrade projects. 4 AC power sources. Our long runtime battery plants provide a good reliability for decades. But both internal and external data indicate that we will achieve substantially higher reliability using the 2N utility and 2N generator model. Our goal was to exceed an MTBF greater than 20 years for the entire portfolio, and we have done that. On ROI, it's hard to calculate the ROI of a negative number. So it's not like an investment you make that you expect to pay back for in years. It's like you get to save the money right now. We eliminated specialized maintenance personnel, automated capacity analysis, inventory and regulatory reports. That really makes my ops manager happy. The second utility improves your reliability more than any other opportunity, and you don't have any maintenance cost with it. Distributed architecture eliminates coincident AB node failures. If I lose power, which would be unusual, but somehow I manage to lose both A and the B power system in the cabinet, well, I have a B-side server that's not in the same cabinet, so it's still alive. Even with this system winning every bullet point, the paradigm shift was still not easy. But once it broke through, this is now our status quo.
Great, thank you, Don. We have some time now for some questions. I really appreciate you taking the time to do this session. Dave, were you going to moderate questions? Were there some questions from the audience?
Yeah, sure. To begin with, is Don, this you mentioned that this approach seems to be a little future-proof as your racks get more and more power to them. So is there a reason why T-Mobile is going to more powerful racks right now?
Yes, the power densities of all modern equipment has gone up substantially. So literally everyone is on the hunt for more efficiency. And as you can see, when the servers improve their throughput in the same size unit, they coincidentally get an improvement in power efficiency for the given amount of work. So earlier they were talking about PUE may not be the best metric. I mean, it's good if you're looking at cooling systems efficiency, but really we want to start focusing on data center efficiency. And that's where, the throughput of a data center, the compute capacity of a data center versus how much power goes into the utility feed. That's really a better measurement.
Right.
Every time,
measure the actual work, right? That's what really matters.
Yeah, it's the work versus the power. And, and for us, we always took the capital approach, the work versus how much does it cost to run it. And so obviously, if you're having to buy new buildings to put more equipment in, that's not good for capital. And if you're having to pay more for power, well, that's also not good. So we have a good motivation.
No, excellent.
Like I say, it's the power efficiency has got to be where it's not even worth pursuing at this time, as far as like the efficiency of deliver power to the cabinet and the efficiency of cooling it. I mean, our annualized PUE is 1.2, and how much better can you really get?
No, good point. So with this in mind, obviously with this capacity, you must gain back some white space.
Somewhat. Oh, sure. So we also we actually went 1 foot taller on the cabinet as well, but we also 30% more cabinet positions, which both of those really added quite a lot of RU to same given white space. And we just don't have all that distribution gear. There's no RPPs, no SPDUs, no extra transformers. None of that stuff is in there. So there's a whole secondary power distribution system that does not exist.
Makes sense.
So we like to land cabinets in there that make money.
Yeah, no, for sure. And is that specifically because of locating the power equipment on the side? We've seen in the past some top mount power supplies and things, but obviously this is a way just the topology of the cabinet helps with this, I presume.
Yeah, that was the breakthrough, I think, was that ABB was able to figure out how to get enough power energy in a battery stored in that space, and how to fit the rectifiers and the batteries into that edge space. So that's just so valuable, because that was previously like unutilized space. Who knows what you'd use it for, and so and you can actually use both edges of the cabinet for power systems if you have to, but we don't have anything exceeding 30 kW at the moment.
Okay. And then so in the system you're using VRLA batteries currently. Have you been looking into, and maybe Paul can help with different battery technologies? We've heard a lot around lithium ion, for example. I know there's some other things floating around that may be of interest to the audience.
Yes, we've looked at a number of different chemistries, and we're evaluating several of them. It looks like lithium has a lot of questions about it. We're continuing to look at those. They certainly offer some energy density advantages, but also there's a lot of concern about their safety.
Right.
Nickel metal hydride is an option that certainly gives better density, but it is a little bit expensive. So it's a matter of meeting the safety and the cost criteria all in the same technology. There are a couple of other technologies that we're looking at as well, but at the moment the VRLA seems to be the most practical and the most cost effective.
Excellent.
Yeah, let me chime in too.
Yeah,
so
sure.
we TMobile looks at every battery technology that exists that pops up on the radar. We examine it. So we start with safety. That was kind of my first quest, was to discover a battery chemistry that would safely live alongside the server and give me the energy I needed. And it was hard to find. We have come across a couple that have promise, and so we're continuing to work on those. And then costs. You have to find an advantage, right? So you never leave the status quo until you have a compelling reason to make the move. And so for us, lithium ion fell off the radar a long time ago. I think a couple of my friends that used to select batteries for data centers no longer get to do that because they pick lithium ion. But anyway, it's a flammable electrolyte. So
Right.
We're probably not going to put that up against a $800,000 server rack.
Understood. Speaking of the servers, is there a question from the audience? Sourcing DC power supplied servers, is that an issue, or are they commonly available now? I don't really know.
Well, so if you were to walk through one of our MSOs, if you're a data center guy and you walk through one of our MSOs, and we run data centers as well, but if you really wouldn't see a lot of difference. So we run the same routers, the same servers, literally the same model number, the same everything. We just bought them, and we've been in that for a while. So telecom offices are no longer time division offices. They're all async. They're all IP. There's almost nothing in there that's still time division. So it is literally the same components. I get a typical funny story. We'll have someone who's trying to get a procurement person, and they're trying to buy a server for project X, and so they say, well, we only buy these in AC servers, and so we talk to them and say, okay, well, can you get the DC option? And say, well, we only buy them in AC. Say, well, okay. So then we hold their hand and go to the website and look, and sure enough, there's a DC input option right there. So they just had never done it before. It's kind of a breakthrough for them. But yeah, the DC option has been around for a very long time, as long as the telephone.
And that's the telecom standard, right? I mean, that's as I understand.
A lot of cable offices and telephone offices run it.
Absolutely. Have you looked into other voltages of DC? I know that NTT, for example, and forgive me mentioning competitors, but they were talking about maybe a 300 volt or 400 volt DC. Anything else? I mean, obviously,
it's a compelling argument, but I did an analysis on that to see could we do it, and quite honestly, one of the things that's most important to us is being able to build it quickly. So when we try to build or expand an office, we need it now. We probably already needed it, and so we're a little bit late. And we prefer to have almost every part that we need available off the shelf. If I can order the breakers I need from the local electrical supplier, that's a good thing. If I ask him for a 400 volt DC breaker, he looks at me cross-eyed. So it has been a few years since I looked at it, but when I checked, there was only one company making those breakers that were suitable, and then the industry was still kind of unsettled on the safety aspects of it. And I think they're putting a breaker on both ends.
I think you're exactly right. Yeah, we of course have a product to fit, but yeah, it was a combination of things where it wasn't quite ready for prime time yet. But yeah. To your point, it does hold some interesting.
Well, you lop off half the conversion, so
right, exactly.
Yeah, which would be kind of cool, but you can't run 400 volts in the server cabinet, really. So I mean, I guess you can, but it changes the safety rules quite a lot.
Yeah, and that notable competitor who is doing 380 volts DC in their data centers is still using a centralized system. So all of the things that Don pointed out about spreading these power systems out within the racks kind of goes back to a centralized system again in the typical 380 volt DC architecture. We looked at it too from the standpoint of what ABB should provide in the DC space, and really we see the advantage of high voltage DC at 380 volts. We call that high voltage, as being to save some of the cabling losses and cable size throughout the building. And we feel that we have achieved that by sticking to the 480 volts three-phase AC. We got similar conductor sizes. We've got similar losses with putting the rectifiers at the load as we've described in this system. So it's achieving the same ends and the benefits of distributing it.
It's actually quite practical to get 60 kW to each cabinet at that level. So
Okay.
Yeah.
I'd also say you probably have, the traditional data center engineered suspender approach. You with a centralized approach, you have a single point of failure. With decentralized approach, if something does fail, you're probably failing smaller. So, take out one server versus a rack versus a row versus a hall, so there might be some advantages that way as well. And certainly 480 volt AC, there's enough of that floating around equipment wise where it's easy to get to, and it makes a lot of sense. I really think
very raw. It's very raw power. So you literally take it from the utility and and run it out to the floor.
Right.
No conversions, nothing.
And the other thing that Don does in his implementation is to use a bus duct for that 480 volt distribution with pluggable or stab-in takeoff points, so that he can move his cabinets around. He can have different takeoff points, and it's all very easy to install and quick and relatively unskilled to change a cabinet position or change a cabinet out for another one.
Now, is that Don, is that the traditional quote-unquote industrial bus duct or the more specialized data center stuff?
I guess it would be data center stuff, so it has a slot in the bottom usually.
Okay,
there's all kinds of contraptions.
Yeah.
The thing is, you can do is no PPE, no electrician required type of staff. I don't know if we'll do that, but it is safe to that level, according to all the entities that care. And so, it's really quick and easy if I wanted to change the breaker in this spot, or I wanted to install a cabinet over there, or, our game changes quite a lot. So I have to change the configuration of the row in each cabinet position. That happens a lot. I'll just say really quickly, too, we didn't have any trouble cooling it. I think that's one of the big questions. So we're using DX Force Air. We're getting 1.2 PUE annualized in Miami. So without an economizer. So if you want to compare numbers, I'll go toe to toe. But the key to success there was really make sure the plenums are fully isolated. So we do a hot aisle containment and do above roof return air. And then we elevated the return temperature quite a lot. So we do a cold room flood at 73 degrees, and then the return hot aisle containment is 97. So, and that was the key to success. Getting 97 degree air to the evaporator was really how we accomplished that.
Now, is this can we use this solution in existing facilities, or is this basically a start from scratch or a new solution?
Well, I'll tell you what, I have 50 retrofit projects on my desk, and every one of them is doing this. So I think it's doable.
It appears to be possible, anyways. No, that's great. I mean, that's what folks are looking for. So if you need to put in, for example, a HPC node or something, or an ML node, then you can do this, get a lot of power in a small space, and utilize things more efficiently.
Yes. Not only can you get a lot of power in a small space, but you can also put it in places where maybe you don't have capacity on a centralized power system, but you do have capacity on your utility. You can just run the utility direct to where you want it.
Ah, okay, yeah. So if your critical power system's getting stressed, then you could always get more power from the utility. They're always glad to sell to you. Well, in many cases.
Almost always.
We're coming up on our deadline, gentlemen. Any closing thoughts there, Don? Or? If not, that's fine. I think this was a tremendous discussion. I think you guys did a really innovative approach, and really nice to see that. So with that, I thank both Don and Paul for helping explain the system used at T-Mobile, and for the audience, we're going to take a 10-minute break now. So refill your coffee, and we'll be back at 11:10 on the East Coast, 8:10 on the West Coast, and talk about system architectures. Thank you very much.